Hello there and welcome to Lower 6 Further Maths A-Level Pure Core 1. We're looking at the past paper from June 2011 one and we're on question 7, the proof by induction questions. So what we're looking to do here is to prove that 3061 to the power of n is equal to 3 to the power of n 0, 3 bracket 3 to the n minus 1, 1. So as with all proof by induction steps, we have to start with step 1, prove true for n equals 1. So left hand side is going to equal 3061 to the power of 1, which is 3061. And the right hand side is going to equal 3 to the 1 times next cell is 0, and then it would be 3. Now 3 to the 1 is 3, take away 1 is 2. Next cell is 1. So 3 to the 1 is 3, 0, 6, 1. So the base step is then complete. Left hand side equals the right hand side. Second step here is to prove, assume true for n equals k. We don't really need to do anything there, but what we can later do is pull in the fact that our theorem works for when n is the value k. The third part is the more tricky part, and that's where we have to prove true for n equals k plus 1. So what we'll do is we'll start off with the left hand side and we'll try and prove that the right hand side is true. So 3061 to the power of k plus 1. Well, the first thing I'm going to do here is split up my powers using rules of indices. 3061 to the power of k multiplied by 3061. I've just split them up here using the rules of indices. The next part is to now use my assumption that I can use this rule for when n is the value k. So when n is k, I can use this right hand side of the theorem here. 3 to the power of k, 0, 3 lots of 3 to the k minus 1, and then 1, and then I'll have to multiply that by 3061. Now looking to now multiply these two matrices together. We're going across the row for the first matrix and down the columns for the second matrix. 3 to the k times 3, that's 3 to the k plus 1. It's effectively 3 to the k times 3 to the 1, where you add the indices together with the same base number of 3. And then that would be 0 times 6, that's 0, so we don't have to add anything on. Going for the second column now, 3 to the k times 0 is 0, 0 times 1 is 0. Now this is where it gets a little bit more complicated. 3 times 3 times 3 to the k minus 1, that's 9 lots of 3 to the k minus 1. And then carrying along the row, 1 times the 6 is 6, so we add 6. And then looking at the bottom right hand cell, the complicated bit times 0, that's 0, 1 times 1, that's 1. So I think what I can do now is I've got these three cells pretty much sorted, the top left, top right and bottom right. Let's just look at the bottom left hand cell now. This is equal to 9 lots of 3 to the k minus 9 add 6. So what I'm going to do here is, well, I'll simplify the back bit next, but first what I'm going to do is split up this 9 into a 3 times 3 times 3 to the k. You'll see why in a second. And then minus 9 add 6 is minus 3. Now, what I'm going to do now is I'm going to group together this 3 times 3 to the k and multiply these indices together, so it's 3 times 3 to the k plus 1, adding the indices together. And then I'll take away 3. The next thing for me to do to make it look something like this at the top, I'll need to factorize out a 3. So it would be 3 bracket 3k plus 1 minus 1. And that's exactly what I want for the bottom left hand cell. I want this n letter to be k plus 1, and that's exactly what I've got here. 3 to the power of k plus 1 instead of the n, and minus 1 after that. So going back to my original matrix here, I have 3 to the k plus 1, 0, 3 bracket 3 to the k plus 1 minus 1, and then 1 in the bottom right, which is exactly what I want the right hand side to be. That's part 3 done. Part 4 is just for us to write a conclusion. But I won't waste your time in writing out a conclusion, but make sure you do in the exam. Make sure that your conclusion also includes n exists in the positive integers. If you don't write that, you will miss out on one of the marks for the question, so make sure that's included in your answer. Our next proof by induction question is one of my favourites. It's these divisibility ones. So let's give ourselves lots of space again and start with step 1 of the proof by induction. Prove true for n equals 1. So f of 1 will equal 7 to the power of 2 minus 1, which is just 1, add 5 is 12, which is divisible by 12. We're looking for f of n to always be divisible by 12, and if it is 12 itself, it's definitely divisible by 12. Part 2 is always assume true for n equals k. And part 3 is where the hard work comes in. We need to now prove true for n equals k plus 1. So what I'll do then is I'll write out f of k plus 1 equals 7 to the power of 2 bracket k plus 1 minus 1, add 5. And what I'm going to look to do now is I'm going to look to fudge around with these indices and use my assumptions somewhere along the lines. This will equal, let's expand the brackets, 7 to the power of 2k plus 1 plus 5. Now what I have to do, in order to use my assumption, I have to get my 7 to the power of 2k minus 1 back in there. So what I'm going to do is I'm going to split this up, 7 squared, and I'm going to pull out 2 of the 7's from this term here. So it's going to be 7 squared times 7 to the power of 2k minus 1 plus the 5 again. You can see here that if I was to combine them back again, I'd add the powers together and I'd get 2k plus 1. But I don't want to do that. I want to be able to use this part of the expression in my assumption so that I can then prove that it's divisible by 12. What I've got here now is 49 times, and now here's when I'm going to do my fudging step. It's going to be 7 to the power of 2k minus 1, add on 5. Now if I want to balance this out, 49 times 5 is 245, so I'm going to need to now take away 240 from my answer so that the number at the end balances out. It's a bit like when you complete the square, you have to then do an adjustment at the end, so you take into account what you've squared already. We've got 49 times 5 here, that will make 245, and then I'll need to take away 240, so I'm left with just the plus 5. Now what I can do here is I can separate this part here. I'll put a star here, and I'll write here that star is divisible by 12 by assumption. And the fact that it's multiplied by the 49 doesn't change the fact that it's divisible by 12. It's just got more factors in there. And 240 is going to be my double star. 240 is divisible by 12. And then I'm going to write, because I have summated or taken away two multiples of 12 here, I must therefore be able to factorise out a 12 from both of these terms, hence having a multiple of 12 in both of my terms, and then in the term in total. So by the summation of two multiples of 12 also being a multiple of 12, f of k plus 1 is divisible by 12. And that's part 3 proved. Part 4, all that asks for you to do is to write out the conclusion, but I shan't waste your time in doing that. Make sure again that you write down this theorem only works for when n is a positive integer. Thanks very much. 6 marks for each of those proof by induction questions, 12 marks in total.